Yes, welcome you all for another presentation on analogous system. On analogous system. So, by the way, we'll see today lecture number 43. Lecture number 43. So, we will continue the previous presentation. If you recall, in previous presentation we have seen one mechanical system, that is mechanical translational system we have seen, and for which I will continue the same. Just I will draw the same example in this presentation also. That is something given like this. So mechanical, it is a mechanical translational system. It is given like this. This already you have in previous presentation, this particular diagram. But however, we are going to do something another analogy today. This is constant coefficient K, this is the mass element, and here we have friction coefficient B, and then on which you have the applied force F of t, and here you have displacement x. Clear? So this for this diagram today in this presentation we will see the force current analogy. Force current analogy we will see. It is force current analogy. Analogy we will see means the electric equivalent circuit of this particular given mechanical system or mechanical translational system. Clear? We will see. So for this again what we need to do is that nothing, it is very simple to solve actually. As I have explained you in the last presentation, you need to mention, you need to write the differential equations first. Clear? You need to write the differential equations pertaining to this particular block, because it is, as this problem has only one block, definitely you should have only one displacement, because we have only one block here. That's why if you have one block, you have only one differential equation. For example, if you have another block, means if you have two blocks in the given problem, then you will have two differential equations. If you have three blocks, then you will have three differential equations. Clear? As I have explained you in the previous presentation, the number of blocks represents the number of differential equations. It is very clear. Therefore, in yesterday's presentation, we have seen that for the same block diagram, for the same example, we have seen that how this particular block diagram mechanical system is, converted into corresponding electrical network, electrical equivalent circuit. Simply it is a RLC circuit, resistance in series with inductance, in series with capacitance, and the input as the voltage, because it is a force voltage analogy we have seen in the last presentation. Today we have considered the same, and we will write the differential equations for this block then first, and then we will apply the force current analogy. Force current analogy. So before going to convert the force into force current analogy, so we must know that, we must understand, or we must know that the information how these mechanical elements, what are the mechanical elements associated in this block. So what are the blocks, what are the elements that you can see here. So basically you have mass element M, clear, and the friction coefficient is B, and then the constant K, spring constant normally, and you have displacement X, and you have applied force F of t. These are the basic mechanical elements we have. These are the mechanical elements. So how these mechanical elements will be converted, or what are the equivalent electrical elements for this mechanical? So here in force current analogy, remember that it is a force actually, I mean mechanical, these are the mechanical elements, these are the mechanical elements. Correspondingly, what are the electrical? What are the corresponding electrical elements? So your M in force voltage, M is converted to inductance, whereas in force to current analogy, something it converts as capacitance. See, it okay. The mechanical block is equivalent to capacitance. C actually in force current, remember that. So M is equivalent to electrical capacitance, electrical element capacitance. Your B is corresponds to, it is 1 by R actually. 1 by R is the resistance, otherwise you can say it is nothing but your conductance, G. Okay, conductance, normally you can write this as G also, but okay, G is equal to 1 by R basically. 1 by R is nothing but conductance. Now, okay, nothing but G actually. Conductance is G, but however, for our simplicity, we will write 1 by R. Okay, B is 1 by R. If you compare with previous voltage force analogy, okay, or force voltage analogy, there B is R only simply, but here it is 1 by R. And K is equal to, in previous case, it is 1 by, I mean 1 by C. Here it is simply 1 by L. 1 by L, remember that, 1 by L. Clear? And your X converts, it is equivalent to flux linkage. Clear? So F of T corresponds to your current, I of T. Force, this force, what is applied force is equivalent to your I of T. And again, if you take the first derivative of X, X dot is nothing but, actually X dot is nothing but your dx by dt. What is X here? X is nothing but phi. Clear? X is nothing but phi. Then if you take the dx by dt there, okay, X dot is equal to dx by dt, or nothing but dx by dt is nothing but, you can write as X equal to phi. That's why that can also be written as d phi by dt. This is called as voltage V. d phi by dt equivalent to V. Clear? These are the basic conversions actually we need to remember. So your mass element equivalent to electrical capacitance, your B, the mechanical frictional coefficient equal to 1 by R, whereas K equal spring constant, okay, that K equivalent to 1 by L, and your X means displacement corresponds to magnetic flux linkage, I mean electrical or whatever it is, flux linkage. Phi stands for flux linkage, flux actually. And F of T obviously corresponds to your current, because it is a force current analogy. These you must remember. Now for this what we need to, so write the differential equation governing to this particular block diagram. So draw the write the differential equations, okay, the differential equation governing to the, nothing but associated, governing to the above block diagram, to the above given block diagram, What will be the, differential equation for this? If you write the differential equation, this could be, it look like, this is your, tell me, what is that? It is m into d square x by dt square, because always the mass element m is proportional to mass element, nothing but the, actually this particular is nothing but the opposing force. M into d square x by dt square is nothing but, it is an amount of opposing force offered by the mass element. So m into d square x by dt square is nothing but, this is the force actually, this amount is nothing but opposing force by this mass element. Therefore m into d square x by dt square plus B into, if you take the frictional coefficient, that will comes as dx by dt. So for frictional, you will take the first derivative of the displacement. Okay, for mass, you have to consider second derivative, means d square x by dt square, second derivative. Okay, then plus k, if you consider k, so k will be k into x only. It is directly proportional to the force offered by the k. Opposing force is directly proportional to displacement. Okay, then is equal to, what is there, f of t. Clear? M into d square x by dt square. This is the force, opposing force offered by this mass element, and B into dx by dt is nothing but the force opposed by this friction. Because of the friction, okay, this much force will be offered by this friction coefficient. K into x is the spring constant. With the spring constant, this much force will be opposed. All these three are the opposing forces basically. These are the opposing forces by these three element: mass element, your constant element, friction element. And all these opposing forces, the sum of the opposing forces equal to applied force according to Newton's second law. So, clear? This is the expression. This expression is called as differential equation. This particular equation is called as the differential equation for this block diagram. This is also very, very important. If you take in UPSC examinations, definitely if it is given this kind of question, there will be two sub points, A, B, or Roman letter 1 and 2, like that. And your first part is compulsorily they will ask the differential equations only. Write the differential equations for this block diagram. Likewise, they will ask in the examination. Therefore, remember this. This is the differential equation. Clear? Now, now what we do? You can call it as equation number 1, for example. Okay? You can call it as equation number 1. Now, in this, now apply the force current analogy. By applying force current analogy, by applying force current analogy to the above equation, So, by applying the force current analogy we have to apply. It is nothing but simply you must write the mechanical element, all the mechanical element will be converted with their equivalent electrical parameters, and correspondingly your d square x by dt square will also be represented corresponding electrical element, and then also you will get one particular another equation in terms of electrical elements. So the mechanical, this is what the differential equation in terms of the mechanical element. Now after applying the analogy, force to current analogy, the mechanical equation or the mechanical differential equation is converted into equivalent electrical element. Okay, you will get another expression or equation, okay, with the electrical elements. So now if you substitute the corresponding elements in this, normally I will write here. What is that? Now your m becomes what? Obviously compare this particular equation. Your m will be c. Therefore this m is nothing but c. Therefore write c here. C into what is? It is d square x by dt square. Now how we can write d square x by dt square? How you write? So d square x by dt square, clear? Okay, d square x by dt square can be written as, clear? Okay, d by dx of dx by dt. Can we write like this? D square x by dt square is nothing but a double derivative. So first you have to find out dx by dt. For that, if you take another d by dx, then it will become d square x by dt square. Therefore, this can be written as d by dx of dx by dt. Well, what is dx by dt? I already explained here, no? Dx by dt is nothing but x is equal to phi. Dx by dt if you take, that is nothing but d phi by dt. Your d phi by dt nothing but furtherly v. Therefore, it is nothing but d by dx is nothing but dx by dt is nothing but d phi by dt. Clear? Why? Because x equal to phi. Your mechanical displacement corresponds to electrical flux. Therefore, dx by dt in mechanical, the in equivalently in electrical it becomes d phi by dt. D phi by dt is nothing but V. Therefore, you can write V. In place of this, you can write V. Therefore, it is dV by dt. Therefore, d square x by dt square is nothing but dV by dt. Clear? Therefore, this entire part now C into dV by dt. Very simple, no? Plus, this is completed. Now, what is B? B is nothing but 1 by R. B is 1 by R. Then, what is dx by dt? Dx by dt. So, here, from here, dx by dt is nothing but equivalent to what? Actually, you can say V, no? You can write V. V by R. What you can say, what you can observe here, if you carefully observe here, you definitely will have to identify one particular small observation here. What is that? We are writing these let us see what is this and what is this quantity. Or third one also I will write, then I will explain what is the thing happening, is there involved in this. So if you see the third one, kx, k is equivalent to 1 by L. It is 1 by L. Then x equal to, what is your x equal to? X equal to, okay, integral of x dot x d by dx is equal to V. Okay, V. Therefore, how you can write? If I want this x, can you write this? 1 by L into integral of what is this? Some V into, I will explain you that. All these are nothing but if you see what is this actually. So this is nothing but if you take the capacitance, say for example voltage VC is the across the capacitance, let us say current. What is VC here? VC is equal to 1 by C integral of I dt, no? Actually, then what is your I value here? From this I can be written as I is equal to take, it is nothing but C into, C will be comes here, then derivative must be taken for this. It is dVc by dt, means C into dV by dt, means what is this particular is nothing but I is equal to V by R form actually. Remember that. So this is the current equivalent. This is the current equivalent of the capacity. This much is the current, because we are converting the force into current. Therefore, all parameters must be current equivalent with respect to that particular element. This is a capacitive element. Then you write, simply remember, in capacitance what is the current? C into dV by dt. That's what this. And second is the R, resistance. So for resistance, this is R, this is the V across it. Let us say I is flowing that. Okay, what is your V is equal to IR as per Ohm's law. Therefore, I is equal to V by R. That's what it is, no? V by R already. Similarly, if you consider the inductance L, let us say VL is the capacitance. Assume that I is the current flowing through that. Then VL is equal to L into di by dt is the voltage. Then what is I? I is equal to VL by, this is VL. Actually, again it goes to 1 by L. And then it is differentiation. Then you take integral. Therefore, nothing but your 1 by L is already there. 1 by L already it is there. 1 by L it is there. What is the integral of V into dt? That's all. That's all. Clear? And that is equal to, I think understood. This is what we are writing actually. So for the given mechanical equation, you just note that you just write the equivalent, either it is capacitance or resistance, whatever it is, and just you write that what is the current equivalent of that. That's it. Is equal to 0. This is what now I will erase this. This is what now your electrical equivalent. This is what your electrical equivalent of for that mechanical equation. Clear? Understood? Very, very simple. Very, very simple. Nothing to feel more difficult in this to understand. Very simple. First of all, you write the differential equation for the given block diagram or mechanical diagram, and then just you see that in current analogy, means force to current analogy, M converted as C. C is nothing but, so for that you need to draw the current flowing through that capacitor. I value you must, this is the I value. Next, current flowing through the resistor, current flowing through the resistor. That expression if you put, your problem is over. Now if you can see, this is basically I is equal to V by R form actually, is it not? All this is I only. Remember that whenever, so sorry, this is I of t, actually f of t, na, right side. This is not 0, it is I of t. Actually force is there in this expression. So that force is converted as your I of t. Your I of t. I of t. Therefore, I of t is equal to everything. So remember that I of t is equal to sum of all these. So now your I of t, the corresponding electrical circuit, means all these elements, if you represent in an electrical network form, this will be like this. Always remember that in current, if you represent the current as input, all elements will be in parallel actually, in parallel basically. Then 1 by R is there, nothing but your, so here R will be there, I mean this is resistance R, you can write, and next is the inductance L, next is the capacitance C. That's it. So this is the I of t, and this is what your electrical equivalent. It is a parallel RLC circuit. It is nothing but is a parallel RLC circuit basically. That's it. It is a parallel RLC circuit. So I of t, if you equate these two, this is the expression form, this is a circuit form. Therefore, this much IT, this IT flows through this circuit, then IT will be, I mean, it will be distributed. So this is your IR, this is your IL, this is your IC, this is nothing but IC, this is nothing but IR, this is nothing but I suffix L. So if you combine all these, equivalent to total current I of t, means that what? All are in parallel. This is what the solution for that. With this is what your force current analogy representation for that simple block diagram. Clear? I think you understood well. Okay, so with this now I want to finish off this presentation, and we will continue the similar kind of examples, okay, in the subsequent presentation. Okay, thank you one and all.